everyone survives yesterday's food. So it's time to start the morning session. Okay, we are very happy to have Antonio Antunes, who is going to tell us about his work on couple minimal models with Connor, who is also here in the front row. Oh, sorry, yeah, and as Francesco is reminding me, there's going to be a group photo taken just after the talk before the coffee break. Yeah.
Hello, test, can you hear me? Yeah, okay, thanks. All right, so let me start by thanking the organizers for bringing us together one more time here. It's been really great. And let me thank them for inviting me to speak about my work. It's really a great pleasure. As Slava said, I'm going to be talking about coupled minimal models. This is work with Connor, who's here. And okay, the irrational word in the title has two meanings. The first meaning is that it might look a bit silly to go back to looking into minimal models in 2023. But the reason why we go back to CFT2 and these simple models is that they are some of the most digestible CFTs. After tomorrow, it might be convenient to take something more digestible, something that we have more control over. But on the other hand, I mean, they are far from solved. There is still a lot to say about two-dimensional CFTs. So the reason why they are easier to treat, of course, is that they, as everyone knows, they have a Virasoro algebra of symmetries, and one Virasoro rep contains infinitely many global conformal primaries. Let me write global primaries. And furthermore, these Virasoro reps are parameterized by a central charge C, which we know by Zamolodchikov that is something that decreases along RG flows. CUV minus CIR is positive. And so this leads to some hope that in this case we are able to classify or very systematically understand the space of CFTs. Of course, the first realization of this is in the case of C less than 1, that was understood in the 80s for unitary CFTs. And for C less than 1, the classification is complete. The theories that exist are the so-called Virasoro minimal models of the title, which I will denote by this curly m with an integer label little m, which runs from 3 in integers all the way up to infinity. So it's an infinite sequence of 2D CFTs that are unitary. And the reason they are called minimal is because they have finitely many Virasoro primaries. Vir primaries. In particular, they are famously labeled by 2 integers, and their left-moving dimensions, let me call them HRS. These are the 2 integers that label the primaries. The fact that they are finitely many is the statement that these things are bounded by M, essentially. So it's very manifest that there are finitely many primaries. And the central charges, of course, there is some very nice explicit formula here that depends on M, R, and S. It's not particularly important, but let me write it anyway, because some of the formulas I'll write later on will look more believable if one reminds how these things depend on M. Very good, so we know exactly the left-moving or right-moving weights, and we know exactly the central charges. Let me also write them, just for completeness. They are all, of course, less than 1, and they follow in this nice sequence that starts at 1/2 for the Ising model and goes up. So for C less than 1, it's true, we can do everything. But then for C greater than 1, Cardi taught us through modular invariance that we must always have infinitely many Virasoro primaries. So for C less than 1, the situation seems a priori a lot more like higher dimensional CFTs in the sense that there are infinitely many primaries. And there are essentially 2 directions to take this into account. And let me make kind of a table here to explain what are the possible situations. So first of all, the simplest, there are 2 things we can do. So first of all, we can have just Virasoro symmetry, Or we might just have some extra bigger symmetry. Let's call it some curly V, which is strictly bigger than Virasoro. And one very studied situation is that we have C greater than 1, and hence infinitely many primaries. But on the other hand, we can recombine them into finitely many V primaries. So there's a bigger algebra. The representation contains infinitely many Virasoro representations. And these are what we call, of course, rational CFTs. So these are theories that have finitely many primaries of some chiral algebra. So here, the column is, of course, what I want to write here is rational. The situation of Virasoro rational we already solved in the first board. It is C less than 1. So we're done. On the other hand, we might be in the irrational situation, where there are infinitely many primaries. And still here, there are, again, two situations. We might have, anyway, an enhanced chiral algebra with more symmetry, chiral symmetry generators, but still have infinitely many primaries, infinitely many V primaries. A simple scenario where these things are understood is, for example, for supersymmetric 2D CFTs with a conformal manifold. And very often one can study points in this conformal manifold that are rational or irrational and so on. So that's one class of examples that is relatively studied, but everything on this side is, to some extent, quite unexplored. And then we get to the corner of interest, which are irrational theories with just Virasoro symmetry. This particular implies that there are no extra conserved currents. And since there are no extra conserved currents, there is a gap in the twist, a Virasoro twist gap, which is strictly positive. So, of course, the twist in the sense of the global conformal symmetry is 0, because the stress tensor has twist 0, and so do the products of stress tensors and so on.
You could have an accumulation
That's right.
situation.
That's right. There could also be accumulation situations. That's also a possibility. Thank you. But this corner here, so first of all, one motivation is clear. We know very little about the right-hand side. And in particular, this corner here is very interesting because the analytic results that we have onto the CFTs generally apply in this corner, even though in practice there are really not many examples that one can point out. So the analytic 2D bootstrap results, for example, one class is what we all know and love as the modular bootstrap. The typical set of assumptions here is C greater than 1, a Virasoro twist gap, unitarity, for example, and maybe the existence of an identity operator. And this situation is already a situation of which we don't know essentially any examples. In any case, let me just say that the prediction is that in such a theory, there exists a family of operators whose twists accumulates to C minus 1 over 12. Okay, we have this kind of predictions, but we don't really have exactly where to test them. A nice generalization of this is the so-called Virasoro light cone bootstrap. This is, of course, much more recent. And this extends the previous results. First of all, let me add that there's an extra assumption here, which is compactness. Compactness just means that the CFT has a discrete spectrum. This is, in fact, the case we are most interested in. So from now on, let's assume compactness in everything I say. And the prediction here, not only it points to the existence of this family of twists, but also it predicts the OPE coefficients asymptotically, predicts the density of OPE coefficients. And it also predicts the existence of some extra Reggie trajectories, which are discrete. They are called, in the literature, quantum Reggie trajectories. And these are closely related to the Reggie trajectories we've been seeing all week, where the twists become additive at large spin. But in fact, in 2 dimensions, since we have to resum the twist 0 contribution from the stress tensors, there is a modification. And what happens is that instead of additivity in twists, we have additivity in Liouville momentum that Victor explained us yesterday. So these P are the Liouville momenta. They are some simple functions of the twists and the central charge. And there are some discrete series of Regge trajectories. So this is some extra prediction that we have for these theories. In particular, let me remind people that when C goes to infinity, the Virasoro algebra in some sense decouples. We just get a global conformal symmetry, and we just recover the additivity in twists. So the usual linear Regge trajectories. So that's the scenario. We have a lot of interesting results, but not very many theories to apply them to and check them and so on. So that's the motivation to consider this coupled minimal model story. So I'm going to move to the setup now, but if there are questions, this is a great time. So, as I said, we definitely want to start with C greater than 1. And a very easy way to get C greater.
Can I ask a question? So for the corner that you're going to focus on, so the main issue is to ascertain that there are actually no extra currents, right?
Right.
So in the corner, in the SUSY corner, so here,
yes.
So which you say, okay, you put it into the irrational and so on. So here it means in this case you actually do know that there are no extra currents. Because maybe you say here there's some V which contains Virasoro, but maybe actually there is some even higher algebra which we don't know, and so in fact it is rational.
Yeah, maybe the status of these situations is not so different from the status of what I will present.
Okay.
Yeah, I mean, of course, these things typically have some spin 3/2 generators, and people make some perturbative computations in the conformal manifold. They check that some currents break, but it's really at the same level of statements that I'm going to make. Or is there something more than that?
I mean, look, you can always be extremely pessimistic, but we have tons of examples, for example, Calabi-Yau sigma models at a generic point on the moduli space.
Right.
Look, I would say that the burden of proof is on you. I mean, these are very generic theories. We have the difference between the upper and the lower box is that in the upper box we truly have no construction whatsoever. In the lower box we have very explicit sigma models. We know a million things about them, and at a generic point it seems far-fetched there will be some enhancement, but everything is possible. There is a milder conjecture. Yeah, I don't know. But no, I think, well, I don't know. I somehow feel that the lower corner is better understood. But there was a weaker conjecture that I think is also far-fetched that you could perhaps try to push, that at the generic point on the conformal manifold, the Calabi-Yau sigma model, you are infinitesimally close to a rational theory. So this would be this accumulation point scenario where you can always get close enough to having a higher conserved current, but at the generic point, it's like how the irrational numbers are infinitesimally close to rational numbers.
Right.
I thought that's believed to be not the case for Calabi-Yau threefold, even though it's the case for K3.
I completely agree, but I'm saying that is at least something a little bit more plausible. To assume that you have genetically significant things.
Yeah, I guess there's this claim by Gukov and Vafa, but I'm not sure the status to which that's actually, how much evidence there.
Okay. Thanks for the comments. Indeed, I am not an expert in this bottom right corner, so thank you. All right, so as I was saying, we want to go to C greater than 1, and a very natural way to do it, well, is to take n copies of some CFT in such a way that the central charge is just additive, and we get something bigger than 1. This is quite traditional, say, in 4 minus epsilon dimensions. We take n scalars, and we look for infrared fixed points, maybe some ON model. This is something quite typical in higher dimensions. Of course, here we want to make statements that are very concrete about 2D, about the existence of Virasoro currents, and so on. So we would be much better off by working strictly in D equals 2 and finding some other small parameter. So that's the class of perturbative models that we want to find. And in particular, starting with bosons in 2D is not such a nice idea. There is no nice perturbative parameter to couple bosons strictly in 2 dimensions. So that's why we go immediately to minimal models. And the simplest thing one can write down is to take the easiest minimal model, the 2D Ising. Let's formally take n copies of it. And let's couple them by some invariant under permutations and under Z2 symmetry deformation, the product of the energy operators. So this is quite a simple thing to do. And since the epsilon operator in the Ising model has dimension exactly 1, well, this operator, epsilon I, epsilon j, is classically marginal in the UV. Let's say here UV. And one can start doing renormalization group and wonder if there are some interesting infrared CFTs with some central charge that is not so far from n/2. But the point is, this is quite depressing. For n equals 2, OK, this is the C equals 1 compact boson orbifold. That's fine. C equals 1 compact boson conformal manifold. But for n greater than 2, there is no CFT. It's just gapped. It's a weakly first-order phase transition. Let me also point out that in D equals 3, this construction is actually very nice, and it leads to hypercubic models. But that's not the case in D equals 2. It just becomes gapped. On the other hand, we can do a small modification that has been studied for a long time now. Slava was pointing out that if instead of coupling Isings, we couple Q-state Potts models, which at Q equals 2 are, of course, just the same thing as Isings, we can just as well add the energy operators. But now there is some region of interest where Q equals 3, and when Q equals 3, the dimension of this operator is now strictly relevant. It's 8/5. And so we might be in a better scenario. So we have the leading order term in the beta function that wants to pull it down and find some IR fixed point. And in particular, while Q equals 3 is not perturbative, because this is a finite distance away from the marginal value 2, we can make this perturbative by considering an expansion in epsilon, which is Q minus 2. In the vicinity of Q equal to 2, the operator is weakly marginal with a renormalization group, and we find some infrared fixed points. And these have been studied in the 90s by Dotsenko and collaborators. And it's a very natural expectation that these are just irrational CFTs with no extra currents. On the other hand, OK, I thought I heard a question, sorry. On the other hand, I mean, to make these very sharp statements about twist cap, we really need to go and prove that all possible currents are lifting, and this is a very complicated thing to do. And in particular, it seems even less plausible in this scenario because the interesting Q equals 3 point, where the theory is unitary, is a finite distance away from the Q equals 2 point. And this epsilon expansion is really around some non-unitary theories. So the perturbative regime is not pointing to the class of theories that we want. We need to jump a finite distance to land on a unitary theory. And so what we did with Connor to find a construction that fixes this problem, and in particular, that keeps the theory perturbative, but at the same time unitary. So we can study some weakly coupled theories that have all the properties we want. We don't need to jump.
Can I ask, so you said it's a natural expectation that these theories are irrational, but we also know that there are a lot of coincidence in 2D RG flows. That happen to land on rational theories. Now, for a given value of n, I mean, first of all the rational compact theories we know of are cosine models, right? And they're orbifolds. Right? There's literally like no other construction. So for given value of n, if you know, for example, the central charge or some additional data about the spectrum well enough, you would just be able to enumerate all the known rational theories around in that range and see whether it agrees or not. This exercise, I suppose, has not been.
I don't think you can really, I mean, there's work by Brandon in this direction, which we'll hear about later, but I don't think there is a complete classification for theories with an arbitrary number of primaries.
No,
For-
I'm saying
of
that
rational theory.
the only rational, the only rational theories that are known are cosine models. And for central charge in the small range, like around 2.38, as in the case of NCO3, there's maybe a dozen, but not too many.
Right.
Right. If you know central charge to sufficient accuracy, you'll just be able to tell whether it is one of these theories or not, in principle,
Yeah.
I would think. Okay, now, of course, there's a possibility of that there are other rational theories that are not of coset type, but if that's found, that's very interesting because that's completely new.
I agree, I agree.
But
No, I agree. This is also an interesting logic, yeah. Very good. So let me move then to our construction of the coupled minimal models. So now, instead of introducing the parameter q, that brings us to the non-unitary realm, we introduce this parameter m of 2 DCFTs that I had talked about in the very beginning. And now we add a couple of relevant operators. One I'll call epsilon. This is quite identifiable. This is the phi13 in the catch labels that I was talking about before. And then there is some other thing we can write down. I'm writing some normalization factors, I mean, just for being a bit sharper, keeping the deforming operators with norm 1. And now what we do is couple the operators 4 by 4. So this is a bit more complicated than what happened here. We were coupling the theories 2 by 2. Now we will couple them 4 by 4. And so the primary we take is this phi12 primary. So this is the formal action of the model. As I said, I mean, it has the nice property that m going to infinity makes things weakly coupled. The reason is that the dimension of this operator, age, is just equal to 1, so delta is equal to something 2 minus epsilon with some coefficient.
Yeah,
Where-
what about the second term? Should there be phi I, phi j?
No. This is just one. It's just it's not coupled. It's a decoupled sum. It's just phi13(1) plus phi13(2). It's really a decoupled term.
And why did you not add that operator, epsilon I, epsilon j? What
Because
was
it's not close to marginal. It's strictly relevant, and we will just throw it away and work with the close to marginal operators in perturbation theory. So there isn't really epsilon. I mean, of course, what we need to do is write down Katz labels.
Okay.
There is strictly a strictly relevant operator I could add, which is phi12i, phi12j. But this is very relevant, so we can just kill it to try to hit the fixed point.
I guess what's not clear, you have two parameters here, n and deviation from marginality.
Yes.
So, for example, sometimes we also have large n limit, which is perturbative, even though the perturbation is not close to marginality.
Very
so
good.
here, do you need both?
No. N is a fixed Let me write this. Very good, thanks. N fixed.
N is going to be fixed.
N
You
fixed can be anything.
Yeah.
And the thing that is making us perturbative is just m going to infinity.
Okay.
This is our epsilon is essentially 1 over m. That's the only perturbative parameter in the game. So as I was saying, the fact that epsilon is 1 over m means that this operator has dimension 2 minus epsilon. This is the famous weakly relevant operator that triggers the RG flow from the mth to the m minus first. So this is completely expected. What's cute here is that this product of 4 operators, their dimension accumulates close to a half. So when you multiply 4 of them on different copies, the dimension also approaches 2 minus something times epsilon. So we have 2 marginal, weakly relevant operators. And I will explain in a second why it's enough to keep these 2. But before that, let me just say one more thing. This coupling has actually appeared before, so work by Musardo in the 90s, where he actually studied this system, but without the phi13. And back then, the interest was on integrable S matrices, so it's quite cute to see this appear again. And another comment is just what is the symmetry of this model? And the global symmetry of this model, well, if we didn't turn on any couplings, it's hypercubic for the same reasons as before. Oh yeah, I can't even write this weird product. Forget about it. You know what it's supposed to be. It's hypercubic, but this coupling, depending on whether m is even or odd, might break some of the Z2 symmetries. So it's hypercubic for m even, and it actually has just one Z2 symmetry for m odd. So that's the situation. And at this stage, I want to move and try to justify in the RG why this is the interesting model to consider and why we should focus on these couplings.
Antonio, just a question. But if you, what about taking that model that you wrote there and taking the large n limit for fixed q? Does this become perturbative?
I would assume so, yes. I think even Bernardo has considered this for a while. I think this would make the model perturbative also.
So can you explain why you do this, which seems to be more complicated?
It's just because I like better having a weakly relevant operator and doing this type of perturbation theory, which is having a linear term in the beta function. I don't know. Okay. Seems more under control. It's the typical situation that we... I mean, I agree with you. This is also something to try, but...
Okay.
Sorry, I mean, the large element, limiting element that fixed Q is sometimes under more control because you can work directly at a fixed point. Just do the usual one over n expansion, but at a fixed point.
That's fair, I agree, but I don't necessarily want to work with a theory with arbitrarily large central charge. In this way, I can construct theories with central charge close to whatever I want. So this gives me more flexibility. Thanks. All right. So the reason why this thing works is the following. The OPE of these 1-2 operators in a single copy of the minimal models is just the identity plus 1-3, and the OPE of 1-3 with itself is the identity plus 1-3 plus irrelevant stuff. So this set 1-2 and 1-3 is closed under OPE for a single copy. And if you play around with the combinatorics of the different copies and you do the OPEs sector by sector, you find that also these operators, epsilon and sigma, they also close under the OPE. So this... Sorry? The mixed term is fixed by crossing, right? So 1-2 times 1-3 is 1-2. Yeah. Very good. So we are in a good situation, and so we can just write down a general beta function equation that will close in two couplings. Let's label them by I. We know this very well from conformal perturbation theory. It's completely general. How should I write this? Yeah, something like this. And of course, in our situation, we have just two couplings under which this system closes, and we can just solve a quadratic equation. And so now I will bring my cheat sheet and copy the beta function equations, because my memory is not as sharp as other people's memory. So let me call this operator sigma, right? And this one epsilon. The beta function for sigma, the linear term is, of course, proportional to something small, as we like. I promise you it's worth writing this down. The sigma epsilon term that Leonardo was complaining about is here. And then there's something quite interesting that is kind of purely combinatorial, which is this factor of n minus 4 choose 2 divided by some normalization times g sigma squared. So sigma generates itself under the OPE, and it generates it without having to have some non-trivial OPE coefficient in a single copy. It's purely combinatorial. And in particular, you'll notice that for n equals 4 and n equals 5, this thing vanishes. So this suggests that there might be some extra simplicity when we have n equals 4 and n equals 5. But for n equals 6 and so on, these equations are generic, essentially almost generic quadratic equations. And for the epsilon, we have something a bit simpler. That's the set of beta functions, and what we can do now is set them equal to 0, solve them, and find the RG diagram perturbatively to leading order in 1 over m. Let me also make another comment, since people are asking a lot about large n. when we take the large n limit after making m small, so that's not the most interesting case, but let's do it anyway. If you take n large, all these terms are suppressed, and the dominant one that stays fixed at large n is this purely combinatorial one. So this means that maybe the large n regime can actually be studied directly, and that would be quite interesting, but we haven't done it. OK, so now let me draw the solutions of the Gelman law equations. Let me find the RG diagram. OK, so it's two-dimensional. Let's put G sigma here, G epsilon here. The UV fixed point of just n decoupled minimal models exists, obviously. Another obvious fixed point is just turning on epsilon and flowing copy by copy to the m minus first. This is certainly a fixed point. And of course, this is the unstable, and this is stable. But with our two couplings turned on, we actually find two other fixed points, which are tricritical. They have some extra unstable direction. And since they are fully coupled, in the sense that the two couplings are non-vanishing, they are likely to be the interesting things. And so the models we are going to study are precisely these two models, these two pairs of fixed points that appear in the infrared of this coupled set of minimal models. So this is the theories of interest. These are the theories where we're going to make claims that have a positive twist gap, or at least looks like it. But before moving to the twist gap, let me just give some basic conformal data results for these theories that we can just compute quite directly from the beta function equations. So for example, the dimension of these perturbing operators, once you diagonalize the matrix, let me fix n, because the formula for general n is a bit ugly. For example, for n equals 4, we get one is relevant, the other is irrelevant, as it should for a tricritical point. And there is this cute factor of square root 6, which, if you are extremely naive, you are very happy about, and you start thinking about irrationality immediately. Of course, this is too quick, but anyway, it smells good. And for n equals 6, which is kind of where we expect the equations to be already generic, we find something that looks even more irrational. It's a combination of two square roots. OK, so it is what it is. The reason why I say this is a hint of irrationality is the following. Certainly, I didn't mention this in the beginning, I could have. So there's this statement by Waffa that if you have a theory with finitely many primaries, then the conformal data are rational numbers. So the H's and the C's are rational numbers. Of course, just the fact that when we expand this at large m, we get irrational coefficients doesn't mean that the thing is irrational. But it does exclude one obvious scenario. If it was the case that these functions of m were just rational functions of m with rational coefficients, which is the case, for example, in minimal models of all types. This is typically the expressions we find. If that were the case, when I expanded in 1 over m, I would certainly not get square roots. So at least at a very basic level, this smells like irrationality. There are two operators, right? There's sigma and epsilon, and when you diagonalize, some linear combination of them gets the plus value, and the other linear combination gets the minus. For n equals 4, yes. For n greater than 4, there are some flippings of the signs, and things are slightly different. Yeah, thanks for asking.
N greater than 5.
N greater than 5, sorry. Yeah, thanks, Connor. And before moving on to the interesting, juicy part about currents, let me also say that, since it's so straightforward, this is standard conformal perturbation theory, one can also compute the shifts in the central charge by using, say, Cardy's sum rule, for example, and we find something that is of order 1 over m cubed. This is standard, even in a single minimal model flow, times some weird function of n with some square roots of some polynomials. So the shifts in the central charge for n large enough, say greater or equal than 6, are also square roots. OK, so the same type of argument applies. So now let's move to the serious part, which is checking whether currents lift or not. Sorry.
So In the case of just the 513 deformation, the flow between minimal models, we know it's integrable because
Yes.
you can construct higher spin currents
Very
due
good.
to the non-relation among the descendants of the deformation operator.
Yeah.
Now, in this case, we turn this other deformation and have both parameters. Do you know that there are no conserved higher spin currents?
It's not obvious, but I mean, even for a single minimal model, when you turn on two operators, the counting argument of this null space just tells you that nothing survives, and so there's no reason to believe that in a more complicated case it would survive.
Okay.
Thanks. Very good. So let me then erase this. How am I doing on time? Yeah, it's okay. So now let's move on to the twist cap. So the question now is whether the twist cap is positive. Certainly, if the twist cap is positive, we're guaranteed irrationality. But of course, the interesting part is whether the twist cap is positive or not. And the reason why we start in a complicated place to check this property is that in the UV, our chiral algebra is very complicated. It's a n-fold product. It's an nth power of the Virasoro algebra, right? Because we just have decoupled theories. And this is a gigantic algebra with a ton of currents. We will write some of them explicitly. Now, if we have this expected situation where we will just land on a single Virasoro algebra, what we will have is some diagonal Virasoro algebra, let me call it Vir hat, whose generator, the obvious candidate, is just the sum of all the stress tensors, right? So each individual copy certainly should not conserve energy momentum separately, but altogether, this is the obvious expectation of a generator that should survive. And so as a first step, let's try to check that actually our chiral algebra is strictly smaller than Virasoro to the n. Let's try to find at least some currents that break. And the obvious point to start with is take the n independent stress tensors that are separately conserved and try to find their anomalous dimension matrix. So compute something of this type, some anomalous dimension matrix of the n stress tensors. And for that, we can just use conformal perturbation theory as usual. So the standard calculation that we are instructed to do, first of all, is to integrate this 3-point function. But this is obviously 0, because this is computed in the UV, of course. This is obviously 0, since these currents are chiral. The operator is a scalar, so this thing just has to vanish. And then we go to second order in conformal perturbation theory, and the objects of interest are integrals of 4-point functions. And this can be done. In this situation, they are actually quite computable, at least for the stress tensors. But since this won't generalize very nicely to the general case of higher spin currents, let me instead quickly remind you of a very nice technique to compute anomalous dimensions of currents, which is this multiplet recombination method. This will be brief. I'm sure many people are quite familiar with it. But anyway, it's useful for notation also. The statement is that we start with some short operator of spin L in the UV, and it becomes, I shouldn't write, I don't want to write UV, I want to write short. And if the current is broken, then in the infrared fixed point, we will land on a long spin L representation. But the point is that there are more states in the long representation than in the short, so what must happen is that the short operator must eat some divergence, some spin L minus 1, and then this can recombine into a long current. What does this mean at the operator level? Well, it just means that the derivative of some spin L current is proportional to some L minus 1 operator with the right quantum numbers. Dimension should be L plus 1, times some coefficient here that will depend on the couplings. And the fact that there are UV conserved currents means that this coefficient starts at linear order. The constant term vanishes, plus order g squared. And the nice thing about this trick is that it buys us one order in perturbation theory, because we automatically get one power of g in front of everything. So let me write down some general equations. So the anomalous dimension in terms of this coefficient b for some current t I can write it as some g square, b square times some norms. I'm being a bit pedantic about norms because we will actually have to construct algebraically by hand these currents, and so it's good to keep track of the norms. But then these b's can be computed by a first-order conformal perturbation theory calculation, which is how this buys us one order. So in principle, we'd have to do 2 integrals, but we actually only have to do 1 because of this. And the reason is that if we compute this 2-point function to order g, well, by the non-conservation equation, it's just a 2-point function of v. But on the other hand, we could bring down the operator, and so it's an integral of the derivative of a 3-point function. And this is completely straightforward. This is just a contact term, and this is essentially proportional to the OPE coefficient TVO. So in the end, these second-order anomalous dimensions of currents are rather straightforward to evaluate. The answer is that they're proportional to the square of this OPE coefficient TVO with properly normalized operators. So this is a much easier computation. All we need to do is to build a T, build the corresponding V with the right quantum numbers to be able to appear on the right-hand side, and then compute a 3-point function, all in the UV decoupled theory. So that's quite straightforward.
Is it? OK.
Yeah.
I thought you wanted to show that the current is broken, and now you're assuming it.
No, I'm just giving you an alternative method to compute whether the current is broken. If this 3-point coefficient is non-zero, then the current is broken.
But to arrive at that formula, don't you need to use the dt is equal to v?
But b is fixed in terms of this 3-point function. I don't assume it from
Okay,
the beginning,
okay,
right?
thanks.
If the 3-point function is 0, then it's not broken.
OK.
Okay?
Thank you.
OK, so let me move on to doing our construction. I remind you that our original goal at this stage was to compute the anomalous dimension matrix of the n decoupled stress tensors. And now we've essentially reduced it to building some vectors vi of spin 1 with dimension 3 and computing their 2-point function by that formula. So let me tell you what these VIs are. They are quite obvious. Because of the conservation in the UV, it's quite natural that they are built in terms of some derivatives of the deforming operator. And let me write this explicitly. Since it's nice in this case, it's not very hard. So we have this phi12 operator in the copy I. We take its derivative. And then let me just adopt this notation phi to be phi12. Let me start suppressing this Katz label, if you don't mind. And then we need to subtract some total derivative to make this thing a primary. So this guy has dimension 3. It has spin 1. So it's the perfect candidate. We just need to compute that 3-point function. It doesn't vanish. And what we find by diagonalizing this matrix is the following. The matrix of anomalous dimensions has one eigenvalue that is equal to 0. And the eigenvector is, of course, the diagonal stress tensor, as it should. It better not lift. And then we find an n-1-fold degenerate eigenvalue, which is equal to g star pi squared 3 over n minus 1. And the eigenvectors are differences of stress tensors, n-1 such differences. For example, ti minus ti plus 1. So this is the basis of such operators.
Sorry, can I ask a question? I think I'm a bit confused by something. So here you wrote a V that has the right quantum numbers to be on the right-hand side. Don't you need to write all such Vs? Why are you writing one?
I mean, because these guys are like identical copies, this I label is just some vector if you want. And I wrote immediately some Vi. And so, of course, I need to compute a matrix of Vi Vjs and diagonalize it.
But just so I understand the logic, in this type of tricks that you are doing there, if you have more than one V, you need to write, I guess, a sum of all possible Vs that could show up, right?
Right.
And so is the statement that this is the only V that could show up, or there are others and I don't care?
For this particular operator, these are the only Vs that can show up.
Okay.
When I go to higher spin, there will be many, many Vs, in fact, many more than Js. And then you need to find the correct linear combinations.
but you really need to find all first. The first step is finding everything that has the right quantum numbers to put on the right-hand side.
Yeah.
Okay.
Sure. I mean, you need to find a basis of linearly independent V's. What we do in practice is we find as many as we have currents, and if they're linearly independent, the rows of this matrix, you are done. If they're not, you keep finding more V's until eventually you find some linearly independent combination, and then you're done. You don't need to build all of them. Thanks, Connor. All right, so I was pointing out that we have n stress tensors. Now we have just one, and we have now two non-conserved spin 2 operators. They form quite a nice multiplet. The reason is because, of course, of Sn representation theory. They just sit in this regular representation of Sn, which is kind of like a vector. So they belong to this representation of Sn. So that's good. At least we don't have multiple stress tensors. We're in the right track. But there's still infinitely many more currents to check, so this is going to take a while. But let's at least go to spin 4. It's the coupling evaluated at a fixed point, sorry. In this case, it's just sigma, because the epsilon is totally decoupled, so only sigma contributes to this calculation. Thanks for asking, João. Sorry?
I mean, you knew there was only going to be one generator of translations after the deformation, right? This whole, like, of course the stress tensors
Of course the stress tensors will lift, yes. But OK, at least you compute their anomalous dimensions, and you check that representation theory is going on, and so on. But yeah, I agree. This is kind of obvious. But now at spin 4, it's very much not obvious, and we need to do an explicit computation. And let me write down for you, just to have an idea of what type of objects appear, a spin 4 Virasoro primary current. So now when I say Virasoro primary, I of course mean Virasoro primary with respect to t hat. So how does this object look like? There's some piece that looks like a descendant, because it's totally diagonal in the indices. It's L minus 2 squared I. Everything is going to act on the vacuum. But then there's some cute piece where we actually sum over different indices, and you have L minus 2i, L minus 2j, this whole thing acting on the vacuum. So this state is a primary state of spin 4. The way we construct it is obvious. We just make an ansatz with all possible terms that are reasonable. We act with L1, we act with L2, we require it to be 0, and then this fixes the primary. So, and we normalize it. Okay. One observation here is that this might look familiar to some people. This is the globally primary spin 4 current in the stress tensor multiplet. Of course, typically it's not a Virasoro primary for a single model, but when you couple all of them together, you can add this piece, and now this becomes a full Virasoro primary. And at this stage, Pedro's question kicks in. How many V's do we have, and which ones will actually make this guy lift? And for generic n, which means for n greater than 4, we actually have two candidate V's. One of them actually has a 0 3-point function.
So I'm confused. Why do you have one for T4 and not n?
Because this is the singlet T4. I'm showing you checking explicitly the singlet current of spin 4.
You want to check that it remains conserved.
I want to check that it lifts, because this is a diagonal Virasoro primary. So if I had a Virasoro primary that was conserved, I'd be in bad shape, because this would have twist 0 and be a Virasoro primary.
Virasoro,
Yeah, of this particular Virasoro, with respect to the diagonal stress tensor. That's the Virasoro we have now. And so we can actually build two separate V's with the right quantum numbers that are primaries. And we can show that one of them actually has a 0 3-point function. So that's the worry of Pedro. But we can go and construct another one, which is orthogonal to this. Let me call it V3. It can be obtained very similarly by acting on the deforming operators with a bunch of permutation invariant combinations of the Virasoro generators. This is absolutely explicit. Some of these computations are fun if you do them by hand the first time. Then, of course, you need to automate them to go to spin 10. So this, you see that it's relatively big ansatz, and it keeps getting worse and worse as you increase the spin. But at the end of the day, we can construct a particular combination which won't have a vanishing three-point function with t, and in the end, this will basically fix the anomalous dimension of this spin 4 singlet current. And at the end of the day, this gamma of T4, once you work out this three-point coefficient, which is non-vanishing, it's also quite a beautiful formula of n. It's just 5n plus 22 to n minus 1. So these are quite clean formulas of n is completely arbitrary. And let me make a comment now that these anomalous dimensions are all suppressed at large n. They are all contain n in the denominator, which once again points to an existence of a good large n limit that would be perturbative. So once again, this is something to look at in more detail. Sorry, it's just the deforming operator acting on the vacuum. So right? Yes, let me be explicit. Sigma is something like sum over permutations of phi 1, 2, phi 1, 2, phi 1, 2, phi 1, 2, and then zeros, and you sum over permutations. It's just the deforming operator. And then you act with L's on the different phi's and the zeros. Thanks. OK, so now we've gone up to spin 4, and unfortunately, we couldn't go all the way up to infinity. We had to stop. And let me show you where we stopped.
Sorry.
Why you don't need all the V's? Sorry. I'm just a bit. Is there a simple argument? Just so I learn conformal perturbation theory.
OK, let me give you the simple argument. I'm going to write it, Peter. So generically, what you have is a big matrix with some TIs. Suppose you fix the spin, and there are a bunch of TIs. Now, this I is not an index of the permutations. It's just a bunch of currents. Let me use a capital index. TIs, and there are a bunch of VJs, and you compute this matrix of three-point functions. And the point is that there are many, 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 many Vs. So it's a matrix that's extremely wide and not very long. And if there was a current that were lifted, it would have to give 0 to all the V's. So there would need to be a line full of zeros. Some linear combination of lines would give 0. All you need to check to avoid this is that all lines are linearly independent. But this is very easy because there are so many V's, you don't need to check all of them. You first check as many V's as you have T's, and if they are linearly independent, you're done. You can never have something that gives 0. But maybe you get something that is independent, and you check one more, and one more, and one more, and eventually you find linear independence because you have more and more columns, and you are safe.
Can you explain the very first statement? Why you have no anomalous dimension, one line is 0?
Because this would be there would be a T whose three-point function with any V is 0. All the three-point coefficients that are proportional, the anomalous dimension is proportional to that OP coefficient, to a sum for all of them, and it would be 0 for all possible V's if you find such a line, which is 0. So now all you need to check is linear independence, and that's how Connor did it quite efficiently. You first build n V's, if n is the number of currents. If you're happy, you're happy. If you're not, you keep going. And in practice, you only have to go n plus 2, n plus 3 at most. So OK, since I have here a table, let me list out.
So at spin 4, you checked all the possible currents, that all the spin 4 currents have anomalous dimensions?
Yeah, for spin 4, this is really the only guy you can build. There's really just one at spin 4. You could build also non-singlets. This is kind of a subtle point. So non-singlets, if you have a non-singlet, you could consider normal order products of that non-singlet, and you would make a singlet. And since they are chiral, and all the currents lift, so if you go up to spin 10 in the singlets, you basically ensure that all the non-singlets up to spin 5 lift, basically. There is a small caveat to this, which we will try to cover. But essentially, if we check a big list of singlets up to spin j, it ensures that spin j over 2 for any representation will also lift, up to a small caveat. The caveat is it could happen that this normal order product is a descendant of the identity. But most likely this doesn't happen, and we need to check it, and we will fix this in the upcoming paper.
So you only check singlets, and then you have this somewhat indirect argument. If you check singlets up to some high dimension, then the non-singlets are taken care of.
Up to half that dimension. So our statement of spin 10 becomes a bit less impressive if you take that into account. It's only spin 5. But
check, rather than constructing these currents with explicit coefficients, you can just count the number of independent higher spin currents versus candidates V's.
right.
That would be presumably much easier.
That is easier, but no one forbids you to have linear dependence. You have to explicitly check that they have a linear, that the rows of this matrix are linearly independent.
I'm just saying, in the case of the integral flow between minimal models, the original argument that didn't require constructing the V's, right?
But that's the opposite. If you don't have enough V's to lift all the currents, you cannot conserve them all.
I understand. I'm just saying that that's kind of a first pass. You know that's the case for this.
Yes,
model?
That's the case. Yes.
Okay.
Thanks. So without checking linear independence, it is true that there are more V's than T's. Thanks. Very good. So finally, let me write how many there are to convince you that this is indeed the most obvious scenario that everything will lift. So as a function of n and j, let me write a few of them up to spin 10. So I will write a pair of numbers, which is the number of t's that are possible and the number of v's. So for spin 4, there are only very few of them, but to give an idea, for example, at spin 10, I'm not going to write the full table. But at spin 10, there are 18 V's and just 5. So you need a 13-dimensional miracle to not have lifting, which is what she is saying. I mean, why should you believe that this happens? But we check explicitly that the miracle doesn't happen. And in particular, as j increases, this becomes more and more obvious. There are just way, way more V's than T's. So this is the reason why we believe that all the conserved currents will lift. There are just way too many divergences to eat them up. But of course, this argument is a finite j argument, and this is perturbative, so there is kind of a little gap, which is to close the argument from the large j side. So what happens for currents of very large spin? This is conceptually the open question that remains from our analysis. And I might say a couple of words in the end about it if there's time.
You have in mind some strange W algebra with a spin 2 current and a spin 250 current.
Yeah. Should I say this now? Let me say this now. OK. I have to stop? Isn't it 1 hour and 15? I thought we were extending the... Yeah. But I mean, if you want, I can stop now. OK, anyway, I was going to say this in the very end, but let me say it now. The large j side. So Balt was suggesting whether there can be some very exotic chiral algebra with a spin 2 generator and then a j that is very large. Do we expect that there is some bound on this? Is this something unavoidable? I can make only one statement. The statement is the following. This is in some paper of the 90s by some Dutch author. I don't recall the name. But the statement is the following. For chiral algebras with only 2 generators, strictly 2, and this is, of course, a very strong assumption, then the situation is as follows. For W2,3, W2,4, and W2,6, these chiral algebras exist, and they have infinitely many central charges in which they are consistent. For J greater than 6, a lot of them exist, to 7, to 8, up to some enormous value. But you can give a very solid argument. It's not watertight, but it's quite solid, that for j greater than 6, they can only exist for discretely many Cs. Cs can only fit in some finite value. And since RMs can be arbitrarily large, and the central charges can accumulate, and this is arbitrarily weakly coupled, I believe we kind of have proved that our theories cannot have a chiral algebra with just 2 generators. But then the question is, well, what if you don't just have 2 generators? What if you have J, J1, and so on? Is there a bound on J, on what is the maximal possible gap between the spins of a chiral algebra? I don't know. Probably the technology from the 90s is going to be way too hard to use here. But maybe there is some numerical bootstrap question to ask that would give us a bound. And that would be very encouraging. It would be very general, because it would give you a general technique to check whether a theory has a twist gap or not. You compute currents up to some large but finite spin, and then you have some bound on the other side that tells you can stop now. That would be the ideal situation. Of course, we don't know if this is the case. No, not necessarily. I don't think so. I don't think so. For example, there are also examples. Okay, apart from the joke, let me point out that there are examples. For example, there are algebras of the type W2, 4, 4, 4. These type of things exist. I mean, I don't know. I don't know, Petra, but that would be great. It's in the strengths of strong generators of chiral algebras. I mean, the normal ordered products of these things generate everything, basically.
Can I ask you a question? So, if you take a fixed large M, to how large J can you go before perturbation theory breaks down?
Very good. So, from that, okay. One argument is from the Virasoro-Lightcone bootstrap side. And there, essentially, the criteria is that where Virasoro-Lightcone bootstrap applies is where square root J times the twist gap are of order 1. So this would suggest the twist gap for us is 1 over M. This would suggest M order root J. That you can trust M order J of, I mean, if you want J of order 1 over M squared.
No, but I mean something much easier than this argument, fancy argument. So you are computing the anomalous dimension in perturbation theory, right? You're only working to one loop.
Yes.
So I'm asking under which limit on J the correction, the two-loop correction is smaller than the one-loop correction. Presumably, if J is extremely large, you cannot make this sort of statement.
Yeah, I agree.
So how does the two-loop scale with J compared to the one loop?
That's a good question. We didn't look at it, but I don't know the scaling of J with M. I mean, the concrete statement I have is this one, but okay. We didn't check higher orders, and it would be important to check to see how far we can trust perturbation theory. On the other hand, if this type of argument exists, maybe I'm not too worried, because however it scales M with J, I make M arbitrarily large, and then I push the J in which I trust arbitrarily large.
How does the one-loop correction scale with J? You found anomalous dimensions for J up to 10. Was there some obvious scaling with J that you found?
There are many families, so it seems to stabilize at large J, so the correction, yeah, we didn't check too much. I can't tell if it's 1 over J or what it is.
Yeah, we didn't find anomalous dimensions for most of these. We stopped as soon as we had linear independence.
Yeah, that's right. That's right.
So then...
Which we know they are non-zero because of linear independence,
yeah.
But for high enough spin, there are just so many. We didn't compute the explicit linear combination that gives the anomalous dimensions.
But that's very interesting because you would like to see, like, is it going down with J or is it stabilizing, as you're saying? So
yeah.
Because you want to make some claim about tau gap.
That's right. That's a good point. We did look at that for another family of operators, not the currents. I can make just a quick plot about that. How is the time? No, okay, I can say a few words about that.
Before you erase this, isn't there one? The first entry in the row for spin 6.
That's right, Connor. Thanks for pointing that out. So for spin 6 and n equals 4, there's actually, in this 2x2 matrix, the two rows are linearly dependent, which means that there is exactly one situation, so far as we've checked, where there is a current that remains conserved to 2 loops. So for the 4-copy model, it seems that there might be some chiral algebra of the type 2,6, maybe comma something else. But this is just like a second order statement. One would need to go to higher orders and check if that particular current stays conserved or not. But it's OK. It's one of these cute coincidences that people pointed out could happen. I think she pointed out in the beginning. And in this case, it looks like the spin 6 current could stay there. Oh, crap. Sorry. This is dangerous. Thanks. You're the best. All right, so that's the last thing I wanted to say. We changed a bit the order, but it's fine. Let me just say that what Slava wanted for these currents, which I agree is the important thing to check, we did for a different family of operators of this type, phi I, phi j type operators, whose twists approach 1. You can put a bunch of L's on these guys and build a spin 2, some type of Reggie trajectory. There are more and more operators at a given spin. And we did compute their anomalous dimensions and plot them. And there's some particularly nice family. So this is the anomalous dimension, L, times M, which is 1 over the coupling, as a function of L. And this thing looks rather messy. There are many, many, many families. There's kind of a dense region. But there's an interesting family where the sphinx looks quite smooth. And they asymptote to a constant plus some power law type correction. L is J, is the spin. I mean, this is some L equals 0 operator. This is some L equals 2. It's some Reggie trajectory of operators that you build with these two phis and some Virasoro generators. This is like some spin 2 double traced, morally, if you want. Then at spin 4, there are already more of them, and so on. I'm just plotting all of their anomalous dimensions, like the plots of Alexandre or Petre and so on. There is one particular family that we identify, which looks very much like a double trace trajectory of the type that Virasoro mean field theory predicts. In particular, at large n, it does become a normal double trace trajectory of the light cone bootstrap style with d greater than 2. And at finite n, we can keep track of this trajectory, and it looks nice and smooth. And these corrections seem more or less power-like. We didn't quite fit them. But OK, something like this would give you an expectation of to what m you can trust J. Ideally, we would do this for the currents, but we didn't do it. So this is kind of the candidate quantum Reggie trajectory described by Virasoro mean field theory. So let me finish now with some things to do. One is already discussed, is to give a bound on the large spin side. From the large spin side, this would be tremendous, because then we can only check infinitely many currents become something rigorous. You stop when you can. Another thing is that I think we kind of established that at least for sufficiently large n, these are good, honest CFTs. And we might just want to study them directly for its own sake. We might want to try to bootstrap them, or maybe use Hamiltonian truncation, because we start from some minimal models. Perhaps even Monte Carlo. So I guess that would be interesting to check like the conformal window in M. One of our M expansions are typically quite nice. We might expect m equals 4 to still present these CFTs, but it would be nice to check the conformal window if you want. Then it would be, as I've said already a couple of times during the talk, to establish some large n at fixed m expansion. That would also be quite interesting and give kind of an orthogonal handle on these models. And finally, with Connor, we've kind of extended this logic of coupling minimal models and finding quasi-marginal operators or weakly relevant operators. We did it for a general Wn, or in fact, more general W algebras minimal models. And there is a quite cute classification of the ways you can couple these minimal models and produce weakly relevant operators. So that's something that should appear also at some time in the future. Thank you.
So can you give an idea this large J analysis that is so far missing? Like, is there some clear path to this analysis, or is it like a wild dream that this is ever going to be shown?
This type of statement?
Yeah, that there are like no chiral algebras with
right.
J larger than 1,000,000 or something like that.
It's probably worth working analytically for maybe 3 or maybe 4 generators and seeing what happens. That's probably doable. But then I think it might be possible to try to do some numerical Virasoro 4-point bootstrap with some external currents of this type, and demanding that they only exchange the stress tensor and themselves, for example, trying to bound the chiral gap with some bootstrap problem like this. It's not completely clear if such a gap exists, or, but I think it's worth thinking about more carefully.
But what kind of statement would you be aiming for? That there are no chiral algebras where the second generator has spin larger than 1,000,000?
Maybe 50?
Well, okay, 50, yeah.
Yeah, that's the kind of statement. Yeah,
but do you think such a statement has a chance to be true? Because if you have to again consider 2 generators, 3 generators, 4 generators, there's still infinitely many possibilities to check. So
that's right.
Are we
but with
going
a
to see this
numerical
problem
bootstrap
solved?
thing, you can include them all at once, right? With some numerical bootstrap, you can just impose a gap. You say this is the first one, and then there can be anything.
Yeah.
If you formulate it numerically, it has a chance to give a sharp answer. But otherwise, I agree with you. It's once again a problem of going on and stopping at some point.
So which numerical bootstrap problem would you suggest to consider? Can you be more specific?
So probably some 4-point function of the current J using Virasoro blocks.
Yeah.
Assume that in the OPE of J and J, you only exchange one stress tensor,
Yeah.
and then this J, you put a gap all the way to J itself.
Yeah.
And
what do you want to show?
And then you show if there is some upper bound on how far you can push J without violating unitarity.
Ah, I see. So you would hope that maybe it's just inconsistent.
Yes.
Okay. Well, that would amount to showing with some computer-assisted way that there are no chiral algebras where the second generator has spin larger than 50 or something.
No, the second, yes,
Yeah.
the second, but then there could be arbitrarily many, right?
Okay.
Yeah, but if you but this exists only for discretely many central charges, so you would fix the central charge in the vicinity of n, which is RUV central charge, and check for a fixed central charge close to it.
Okay. Okay, yeah, well, this gives some hope.
I'm not sure. You know, these W algebra, if they exist, they hinge on extremely detailed null states that will happen at a very specific value of the central charge. So you're not going to convince anybody with numerics.
But at least for these examples, it's always like negative rational central charges and maybe one value below 1, which coincides with some minimal model, maybe c equals 1. It's typically not like, especially in the large C regime, right? Maybe the large C region is the most convincing one. But yeah.
We can't hear you.
Right, good point.
I was just saying that if some numerical bootstrap stuff like was suggested works, then the functional probably will work not just for the central charge exactly that you put in, but also in some neighborhood of that,
So
and then you could cover by this.
Right, around the accumulation point. Yeah, thanks, Petr.
Couldn't you, since you have the large L dependence of these multi-twist states, couldn't you fit that power law, and that should be related to the twist gap?
Yeah.
And you have the twist gap for a bunch of states, so if you saw that matched one of the states you'd already found, that'd be evidence that you'd already found the smallest gap.
Thanks, Liam, that's correct.
So can you be more concrete about this numerical? So if you want to do Monte Carlo or Hamilton, which model should we look at? It's like n equals 4? With
I would take 5 copies of 3 critical leasings.
5?
5, because...
4 you don't like?
4, There's this possible extra current. Yeah. That seems like the safest option. Of course, you could try to minimize computational effort and just do 4 copies of Isings. But, I don't know. The logic of the phase diagram that I drew is that there is a stable fixed point that went from some multi-critical model to some model with 1 less relevant. So we should probably start with 3 criticals. That seems more reasonable.
5 tricriticals, that's the minimum.
But maybe Bootstrap, with some, in 2 dimensions, with this hypercubic symmetry, you might just find some kinks. One point I don't think I mentioned, in the epsilon expansion, these theories with discrete symmetries like hypercubic and so on, there's no reason why they can't survive down to epsilon equals 2, or even in the multi-critical expansion around 3 minus epsilon. They might also survive down to d equals 2. And that might be an alternative way to reach these fixed points.
Just so I understand, so suppose that in this calculation that you did, you found a pattern that shows that for any j, you can construct the required number of v's that are where the rows of the matrix are linearly independent. That would still not be good enough, right? Because of Slava's
right,
comment.
Because at some large j,
it would be
perturbation theory breaks down, and that's why we want to close it from this large j argument. Yeah.
Is it obvious it breaks down?
There should be some corrections from this trajectory in some j to some power of m, and some scaling of j with m. This is the simplest thing I can say from Virasoro mean field theory. For example, the physics of Virasoro mean field theory trajectories is different from our physics in that trajectory. So there is certainly a regime where m and j cross with some power that the physics changes. So that's for sure. Because we can predict the twist of that trajectory using Virasoro mean field theory, and it disagrees, except at large m. And the reason it disagrees is because it's in a totally different regime.
Could there be several regimes? Like j scales like m to some power, there's something happens, scales like m to some other power, something else happens, so then closing it from large j would also not be good enough because of...
You can always close from large j because for m large enough, j will also be arbitrarily large. So if there is a finite bound in j, you will always be able to make a sharp argument.
So I just want to contrast this to the case of the supersymmetric Simulon Clavial target space, which can also be viewed as deformation Palomino models, or refolded by a twist field, starting from the Gettner point. And if you run this logic, in that case for the exactly marginal deformation, I'm wondering what would be the conclusion that one can reach?
There is some work on situations of that type with coupled n equals 2 minimum models, worked by Bellin, Castro, and so on. And the conclusions are, qualitatively similar to the ones we find. So that's all I can say with this weakly marginal deformation that in the conformal manifold. Yeah.
Let's thank Antonio.
Thanks. You helped me a lot.
Okay, and everyone, let's go out to